The current electricity chapter is the basics for this chapter. Okay. Yes. Let's start the chapter. Statement 1. Biot-Savart's law gives us the expression for the magnetic field strength of an infinitely current element of a current conductor only. Statement 2. Biot-Savart's law is analogous to the Coulomb's inverse square law of a charge q, with the former being related to the field produced by the scalar source, that is ideal, while the latter being produced by the vector source q in the okay. See, in the first statement what they have given, according to the Biot-Savart's law, the expression of the magnetic field strength, that is ideal of a current carrying conductor only. It is for the current carrying conductor only. Yes. What does the Biot-Savart's law tells us? See, the Biot-Savart's law is applicable for that only. That is, according to Biot-Savart's law, magnetic field to a small element that is given ideal is given by, that is, dB equal to mu naught ideal, that is small current ideal cross r divided by 4 pi r cube, right? This is what Biot-Savart's law tells. Thus we can say that current element ideal, and the equation what the statement applying, okay, that is given by the Biot-Savart's law. So it is the first one statement is correct. In the second statement, Biot-Savart's law is analogous to Coulomb's inverse law, square's law, okay, of a charge q, the former being a field produced by the scalar source ideal, while latter being produced by the vector source q. Okay, what they are telling, they are telling this ideal, this ideal is the scalar they are telling, and the charge q with respect to that Coulomb's law, which is a vector they are telling. Okay, this is q is a vector's law. When it comes to this ideal, here they have given it's ideal cross r. The within the bracket it is a ideal cross r, not a, it's a dot product. So we can say that the ideal in the Biot-Savart's law denotes the vectors. So from this we can say that option, that is statement 1 is correct, whereas statement 2 is false, right? According to us, the option is correct answer is B. Yes, moving on to the second question. A long solenoid of a radius 1 millimeter has 100 turns per millimeter. If a 1 ampere current flows in the solenoid, the magnetic field strength at the center of the solenoid is. See, you know how the solenoid is present, The solenoid is a coil of a multiple structure. It's like that. What they are asking, they are asking magnetic field at the center of this solenoid. To find, the basic formula, that is B is equal to B at the center of the solenoid is a mu naught Ni, where N is a number of turns per unit length, where capital N is, that is denotes small n, and length is the length of the solenoid. Mu naught is a 4.2 10 power of minus 7. If you apply the same, mu naught is a 4 pi into 10 power of minus 7 into N. N means number of turns per unit length. What they have given? That is 100 turns per millimeter. That thing, millimeter means it comes to the, when it comes to meter, it will be 10 power minus 3, right? Into length. What is the length of the solenoid? Length of the solenoid is given, that is 1, right? Yes, 1 meter, like that. So if you do the calculation of this, the 10 power minus 3 goes upside. 10 power of 5 with combining 10 power of minus 7 plus 10 power of 5 into 10 power of 5, which will be 10 power of above will be left with the 10 power of minus 2, and again we will be left with the 4 pi here. So 4 pi into 10 power of minus 2, where magnetic field unit is a Tesla. So 4 minus 2 t. So the, you can see the option is not there. try to write that. See, pi is equal to 3.14, right? Multiplied, which will be 12.56 into 10 power minus 2 Tesla is the correct answer. So option A is the correct answer. See, if they are asking the magnetic field at the center of the solenoid, means the formula is B is equal to mu naught n L, where n is the number of turns per unit length, where L is the length of the solenoid. Okay, mu naught is a 4.2 power of minus 7. Moving on to the next question, that is third question. From the Ampere circuit law, for a long straight wire of a circular cross section carrying a steady current, a variation of a magnetic field in the inside and outside region of the wire is. How the variation of a magnetic field occurs in the straight wire? In the straight wire, how is the variation occurs? They are asking according to Ampere circuit law. See, for example, if I take this wire as a reference, it's a midline where I can put a point here for inside to find inside there, and I take a surface also here, and also outside the surface also I'm going to take a reference here. Yes, just I'll explain to you. Keep it in your mind. Okay. See, we know that the magnetic field at you know the magnetic field B versus R. You know this basis of, if I can understand you, the magnetic field at the center of the solenoid is at 0. Okay, but when it goes to the surface, it is linearly increasing, directly proportional to R inside the surface. And after that, if you consider this capital R as a surface, it will until that it will be increasing. What if smaller, that is outside the surface? Let me consider this point. This is a small r, and this is a capital R, small r, where it is inversely proportional to the smaller. That is, P is inversely proportional to smaller in the outside the wire. So the graph goes like a decreasing graph. That is, B is inversely proportional to smaller, whereas here B is directly proportional to capital R, and B is 0 at the origin. This is what the explanation for this question. So options are given: a linearly increasing function of a distance r up to the boundary of the wire, and then decreasing one with the 1 by r dependence on for the outside region. The option 2, which explains this topic clearly. So the option 2 is a correct answer. Yes, moving on to the next question. Fourth question. A thick current carrying cable of a radius r carries a current I uniformly distributed across its cross section. The variation of a magnetic field due to cable with a distance from my axis of a cable is represented by. See, just now I have told how to solve this question. No, same they are asking how the graph will vary for the magnetic field inside to the outside. Just we now told magnetic field at the center is 0 towards the surface, linearly increasing. After that, while going outside, it is inversely proportional to the radius. Okay, this is how it works. Yes, moving on to the next question, that is fifth question. A long solenoid of a 50 centimeter length having a 100 turns carries a current of 2.5 ampere. The magnetic field at the center of the solenoid is. Again, this is also same type of question that we have solved. B is equal to mu naught n I, where mu naught is a 4.2 10 power of minus 7, n is the number of turns per unit length, I is the current. So they are given a data that is 50 centimeter length. Okay, is equal to mu naught n L. Okay, they are given that B is equal to mu naught n I, mu naught n I. Okay, as for this, the what you substitute, that is 4.2 10 power of minus 7, 4.10 power of minus 7 into number of turns per unit length. What they have given? See, number of turns will be 100, right? where length of it is given 50 centimeter. We can write in terms of meter as a 0.5 into I as the current they are given. There is a 2.5 they are given. See, below it is a 0.5. So on power of 10 it goes upwards. So above 1000 and 10 power of minus 7, which will be 10 power of 4 and 10 power of 4, which will be 0.5. So it will be finally after calculation we will be getting, that is, if you multiply that with a pi value, then we'll be getting 6.28 into 10 power of minus 4 Tesla. Do calculate it because I have told it is in the first case like that only. Okay, solve like that only. Next sixth question, which is based on the toroid concept. Okay, two toroids 1 and 2 have a total number of turns 200 and 100 respectively, with the average radii 40 centimeter and 20 centimeter respectively. If they carry a same current I, the ratio of the magnetic field along the two loops, the ratio of magnetic field they are asking, and toroid also they are given. They are comparing with the two toroids, okay, which having the turns like the data given here 200 and 100, and also radius 40 and 20. Current is same. Important point is they are telling same current, that is I. Ratio of the magnetic field of toroid is, see, for the toroid, the basic formula for the toroid, that is B is equal to mu naught Ni by 2R. B is equal to mu naught Ni by 2R, 2 pi R. If it is so, B is equal to mu naught Ni by 2 pi R. They are asking for the ratio, that is B1 by B2. And just observe the thing, that is mu naught is the same for both, so it will cancel. Also number of terms are different. So for the B1 they are given 200 and B2 they have given 100. Okay, next current they have given the same, so current will cancel, and 2 pi which are constant value cancel, and the radius they have given, that is the radius for the first one is a 20 centimeter, and is of radius of the B1, that is 40 centimeter, and the B2 is a 20 centimeter, which are inversely related. So we have inversed them directly and put in the equation. If you solve this, 0 cancels here, 100 units are cancelled here, so 2 jar, so it will be after cancelling all them, it will be 1. There is a B1 by B2 is a 1. The meaning of that is they have made a toroid such that number of turns for the A as doubled, whereas the radius of that is also doubled, then which is inversely related. So they will cancel each other and giving to a ratio as a 1. Yes. Moving on to the next question. That is moving on to the next question. It is eighth question. A cylindrical conductor of a resistance R is carrying constant current. The plot of a magnitude of magnetic field B with a distance d from the conductor is correctly represented by. Again, it is the same question. This graph is going to be repeated several times. So the again option is B is the correct answer. Yes, moving on to the next question. That is ninth question. A long straight wire of a radius A carries a steady current I. The current is uniformly distributed over its cross section. The ratio of the magnetic field B and B dash at a radial distance A by 2A respectively from the axis of the wire is. Okay. See, it's a long straight wire concept where radius is given an A and current I and uniform distribution they are telling.